Hello, viewers. In today's session, we are going to discuss another important problem from indefinite integrals using the concept of partial fractions, right? And here we have to evaluate this indefinite integral. Let us take this integral as I. And here our integrand is a rational function, right? A rational function, say r of x, is given by p of x divided by q of x, where p of x is a polynomial and q of x is also a polynomial, right? So here our integrand is a rational function, that is x square plus 1. This is a quadratic polynomial. The numerator is a quadratic polynomial and the denominator is the product of three linear factors of this form, say x minus a, right? So here we have x, which can be written as x minus 0, and then we have x minus 1, and then we have x plus 2. So we have the denominator comprising of three linear factors of the form x minus a, x minus b, and x minus c. So here we have x minus 1, and x plus 2. So the degree of the numerator is 2, and the degree of the denominator is 3, because when we multiply these three linear factors, then we have a cubic polynomial, right? And here we can easily see that the degree of the numerator is less than the degree of the denominator, right? So our integrand, that is r of x, is of this form. So here we have, say, p of x, and in the denominator we have the factors, say, x minus a, x minus b, and here we have x minus c. And this polynomial p of x has degree less than the degree of the denominator, right? So whenever we have an integrand of this form, then the decomposition of this rational function into partial functions may be written like this. That is, we have a over x minus a plus b over x minus b, and c over x minus c, right? And here we have to remember that this p of x is a polynomial whose degree is less than the degree of the denominator, that is the degree of q of x. So now, as per this rule, we can decompose our integrand into three partial fractions, that is a over x minus a, and x minus a is x minus 0, that is simply x, and then we have b over x minus 1, and then we have c over here we have x plus 2. And remember, here we have the capital C, and here we have the small c, right? So in order to distinguish between these two c's, right, this is capital C and this is small c, right? So now we can write this expression as taking the LCM of these three linear factors. We have x minus 1, x plus 2. So here we have now a times x minus 1, x plus 2, because when we divide x minus 1, x plus 2 by x, then x and x get cancelled, and we have x minus 1, x plus 2. And similarly, here we have b times, in this case x minus 1 should be excluded, so we have x and x plus 2, right? And then we have here c times, here x plus 2 is now excluded, so we have here x, we can write it over here. So we have c x, and we have x minus 1, right? So now from these two sides, that is the left hand side and the right hand side, we can now equate x square plus 1 with this numerator, that is x square plus 1 is now equal to a times x minus 1 x plus 2, then we have b, and we have x times x plus 2, and then we have c and x minus 1. So now from this expression, we have to find out the values of a, b, and c. So now to get the values of A, B, and C, we'll adopt the method of comparing the coefficients of x square, and the constant term on both sides, right? So here x square plus 1 can be written as x square. Here we can take the coefficient of x square as 1. Then here we can write 0 times x, and here we have a 1, right? So x square plus 1 can be written like this, and here we have now a, and we can multiply these two binomials. So we have x square, then we have 2x minus x, that is simply x, and then we have minus 2, then we have b. We can multiply here, we have x square plus 2x, and then we have c and x square minus x, right? So now we can write 1x square plus 0x plus 1, and here we can now collect the coefficients of x square, x, and the constant term. So we have now a, here we have ax square, here we have bx square, and here we have cx square. So we have a plus b plus c, and we have x square, right? And now collecting the coefficients of x, we have here ax, so we have a, then from here we have 2bx, so we can now write 2b, and from here we have minus cx, so we have minus c, and here we have x, and the constant term is minus 2a, right? So here we have minus 2a. So now if we compare the coefficients of x square, x, and the constant term on both sides, then we can get here three equations, right? So now here 1 is equal to a plus b plus c. So here we have a plus b plus c is equal to 1, and this is our equation 1. Then here the coefficient of x is 0, so 0 can be equated to a plus 2b minus c is equal to 0. This is our equation 2, and the constant term 1 can be equated to minus 2a. So we have minus 2a is equal to 1. This is our equation number 3. So now let us solve these three equations simultaneously and to get the values of a, b, c. So from equation 3 we can now write the value of a is simply a minus 1 over 2, right? Now here if we add equation 1 and 2, then we can see that plus c and minus c get cancelled. So adding equations 1 and 2, we can see that c and minus c get cancelled. So we have a plus a is 2a, and b plus 2b is 3b, and here 1 plus 0 is 1. So now we can substitute the value of a as minus half. So we have 2 times minus half plus 3b is equal to 1. So here we have minus 1 plus 3b is equal to 1. So 3b is 1 plus 1, that is equal to 2. So b is 2 over 3. So here the value of b is 2 over 3. Now substituting the values of a and b in either equation 1 or 2, we can easily get the value of c. So here taking a is equal to minus half and b is equal to 2 by 3 in equation 1. So we have now minus half, then we have 2 over 3, then we have c, that is equal to 1. So now we can write 1 plus half minus 2 over 3. So here we can take 6 as the LCM. So here we have 1. So here we have 6. Then we have 3. And then we have here minus 4. So this is 9 minus 4 is 5. So we have 5 over 6. So the value of C is 5 over 6. So this is how by comparing the coefficients of x square, x and the constant term, we can find out the values of a, b and c. So now we can write our integral I as here we have x square plus 1 over x times x minus 1 x plus 2 dx. So we can now write here the value of x square plus 1 over x, x minus 1 x plus 2 as this expression, right? So here we have a over x minus a, that is simply a over x. So we'll take this expression, right? So we have a over x plus b over x minus 1. Then we have c over x plus 2. And here we have a dx. So now we can write the values of a, b, c. So we have minus 1 over 2 and x. Then we have b, that is 2 over 3 x minus 1. And then we have c, 5 over 6 and x plus 2, right? So we have now three integrals here. So we can now write here minus half, taking the constants outside the integral. We have dx over x, right? Dx over x. Then we have plus 2 over 3. And here we have dx over x minus 1. And then we have 5 over 6. And here we have dx over x plus 2. And c is the constant of integration. So now the value of our integral I is given by minus half. Here the integral dx over x is simply log of x. And here we have 2 over 3. The integral dx over x minus 1 is log of x minus 1. And here we have 5 over 6. And the integral dx over x plus 2 is a log of x plus 2, and c is the constant of integration. So here we have used two important results. The integral dx over x is a natural log of x, and the integral dx over say x minus a is natural log of x minus a, right? So here we can also use the mod sign, that is mod symbol. That is, we can also write minus half natural log of mod of x, and 2 over 3 log of mod of x minus 1. And here we have 5 over 6 and log of mod of x plus 2 plus c, right? So the integral dx over x is natural log of x, and integral dx over x minus a is log of x minus a. So here we have x minus 1, that is 1 over x minus 1. So its integral is natural log of x minus 1. And similarly here we have integral dx over x plus 2. So again, using this result, the integral of this function 1 over x plus 2 is log of x plus 2, right? So the value of this indefinite integral is given by this expression.